Hello, AP Chemistry 12. This is Mr. Chan. And what I wanted to do today was I wanted to expand a little bit on equilibrium, talking about enthalpy and entropy. Now, remember when we did equilibrium, right at the very beginning, we talked about how chemical systems tended toward minimum enthalpy and maximum entropy. So what I wanted to do today was I wanted to focus on entropy a little bit, and then how enthalpy and entropy are related. Now, for those of you that took AP Chemistry 11 Honors last year, we had already talked about enthalpy, okay? We had talked about enthalpy before already, and these were back with the notes, thermodynamics. So what I wanted to do was, I just wanted to focus on entropy. Now, recall from the introduction to equilibrium, reactions generally proceed to a lower state for it to be considered spontaneous. So when we talk about a spontaneous reaction, what it means is that it's reactions that occur without any outside intervention. Like an egg dropping or diffusion of perfume, if you left a bottle of perfume out, it will naturally dispense or disperse without you having to do anything. Same thing with an egg dropping. If you roll an egg off a table, it will naturally drop. That's a spontaneous reaction. Now, if a reaction is considered spontaneous, the reverse reaction is considered non-spontaneous. It requires energy for it to proceed. So if we were to do the example of the egg, if the egg drops onto the ground and we're picking that egg back up, that egg requires energy to go from a lower level to a higher level. So that's why it's considered non-spontaneous. Another factor that helps determine whether or not a reaction is spontaneous or not is the system's entropy. So entropy is the amount of or degree of randomness in a system. It is symbolized by the letter S. So what does S stand for? It's basically spontaneity. Now, again, be aware this is talking about the system. And we've done this before when we talked about enthalpy, when we talked about it from the point of view of a system. So that is why delta H, when we calculate it, is from the point of view of the system. Like enthalpy, entropy is measured by the change in randomness in a system. Okay, so for delta S, we take a look at the randomness of the particles in the final versus the randomness or spontaneity in the initial, and we take the difference between the two. And depending on whether or not delta S is positive or negative, the system is more or less disordered. And notice the key word here, again, is system. All right? Now, again, back in chemistry 12, the equilibrium, we talked about low entropy and high entropy. Low entropy is when you have particles that are a solid, less particles, or low temperature. That would be considered lower entropy. Higher entropy would be like a gas, or more particles or higher temperature. Now, one thing for you to be aware of is this. Particles are always moving. Okay, there's always some randomness in the particles. Now, for example, why is that particles, even if they are by themselves, what happens is there's different types of randomness. There's something called translational movement, and this is where one particle hits another. The particle itself undergoes a rotation or a vibration due to the movement of the electrons. And sometimes there's even electrostatics, where there's movement between the particles due to intermolecular attraction. So one thing for you to be aware of is that there's always going to be some sort of entropy. Now, again, we had talked about this. All reactions tend toward minimum enthalpy and maximum entropy. We have done that, okay? Now, one thing for you to be aware of is this. Spontaneity always follows the second law of thermodynamics. In a spontaneous reaction, there's always an increase in the entropy of the universe. Okay? So how do we calculate the entropy or the randomness of the universe? We take the randomness of the system and we add it to the randomness of the surroundings. Now, again, notice the term system. So when we talk about the system, we're talking about the reaction itself. Okay? And when we talk about the surroundings, this is what we see or feel. And these are our observations. Okay? Now, when we combine the two, what we have is we're able to figure out the entropy of the system, or of the universe, sorry. Okay? Now, but there are times when delta S of the system and delta S of the surroundings are in opposition to each other, such as the vaporization of water. Therefore, which one dominates to determine delta S universe is dependent on the heat flow and the temperature of the surroundings. Now, what do I mean by the vaporization of water? Now, so an example would be like this. So if we go from H2O liquid to H2O gas, that is the vaporization of water. Okay? Now, how do you go from liquid to gas? What happens is, again, this here would be the system. Now, you folks know that to go from liquid to gas, you need to have energy put in. But what happens to the surroundings? The energy comes from the surroundings. And so what happens is this. You get a decrease in energy. Okay? So what happens is, yes, the water particles get more energy, therefore become more random. But where does that energy come from? It comes from the surroundings, and the surroundings lower the energy, therefore becomes less random. And this is what I mean by they are in opposition of each other. So as one goes up, the other goes down. So depending on which one dominates, then you can determine delta S of the universe. Now, it makes sense, because let's say if we are drying our clothes dry a lot faster in the summertime than in the wintertime. So that's what I mean by it depends on the temperature of the surroundings. So therefore, exothermic reactions, what happens is the delta S of the surroundings, you get an increase in quantity of heat or temperature, while endothermic reaction, the surroundings, you have a decrease in quantity of heat over temperature. Okay? Now, so notice here I'm looking at the delta S of the surroundings. It's dependent on the heat flow, so whether the heat goes in or goes out. and divided by the temperature. Now, if we were to express delta S surroundings in terms of delta H, delta S surroundings would be negative delta H divided by temperature. And the minus sign is required because delta H is determined with respect to the reaction system. So recall, so another way you could think about it, delta S surroundings is opposite of delta S system. Okay, makes sense. If we look at this example of water, as the water energy goes up, the energy of the surroundings go down, and vice versa. Now, let me give you an example here. And so what I would like you to do is, if you can turn to page 824 in your zoomed all text. And what I'm going to do is I want to go over question number 35A. So if I to do this, so it says page 824. I would like you to do question number 35A. So it says here, given the values of delta H and delta S, which of the following changes will be spontaneous at a constant temperature and pressure? So what we have here is we're looking at the delta S of the universe is equal to delta S of the system, of the surroundings, plus the delta S of the system. Okay. Sorry, I was just interrupted for a second. All right. So if we're looking at the information there, what do we do to fill it in? So here we have delta S surroundings. We can substitute that to negative delta H over T plus the delta S of the system, in this case, is plus 5.0 joules per Kelvin. Okay. So then what we do is we fill in the data, delta H negative. So that would be negative 25,000 all over 300 Kelvin plus 5.0 joules per Kelvin. Now be aware the units for delta H was in kilojoules, and so what I had to do was I had to flip it to joules. So if I had this, so 25,000 divided by 300, so what I have is negative 78.3, okay, joules per Kelvin. Now, because delta S universe is negative, therefore, reaction is non-spontaneous. Okay. Now, another way to calculate delta S is by using experimental measurements of the variation of heat capacity with temperature. One can determine the absolute entropy for many substances. So when we talked about, one thing we want to talk about is something called molar entropy, or values at standard state. remember standard state is 1 molarity, 25 degrees Celsius, and 101.3 kilopascals, is denoted by S naught. Now, this can be found on appendix A19, and what you will see on page A19 is a data table with the standard entropies. Let's see if I have it here. Here we go. Now, so if you take a look on page A19 in your textbook, what you will get is you will get this thermodynamic data. And you notice in the last column, you have your delta S. Now, a couple of things when you're flipping through this appendix for you to be aware of. Okay? Molar entropy values, standard molar entropy for elements is not 0. It goes back to the fact that the particles are constantly moving. Standard molar entropies for gases is greater than that of liquids and solids. Makes sense. It has more randomness. Standard molar entropies increase with their increase in molar mass. Okay, the larger the particles, the larger the chance of randomness, because there's more electrons, more electrostatic repulsion, that sort of stuff. And the standard molar entropies increase with an increase in number of atoms in the molecule. Okay? Now, an entropy change in a reaction is given by delta S is equal to the sum of the moles of the entropy of the products minus the sum of the moles of the entropy of the reactants. Now, this should be familiar. This is like, if I were to say here, like calculating enthalpy. For those of you who are in Chem 11 honors, you will remember when we did enthalpy, I think we had like Hess's law, and we had the delta H of a reaction. Okay? And so what we want to do is, this is very similar. And again, it will be given to you on your test. Okay? So if we look at this, okay? So what we're going to do is I want to do question number 45A in your Zoom doll text. So if you take a look at question number 45A on page 825. So if we take a look at 825, number 45A, it says predict the sign of delta S, then calculate delta S for each of the following reactions. So you have 2H2S plus SO2 gas gives us 3 sulfur solids and 2 waters. All right. Now, if you take a look, you notice you can predict that the delta S sign will be negative. The reason being is you are going from a gas and gas phase to a solid and gas phase. Okay? Something for you to be aware of. So you can predict that it's going to be non-spontaneous or negative, okay, because you're lowering the entropy. So here, if we did the calculations, so we would say delta S naught would be sum of the products of S naught minus the sum of the reactants. Now, in your textbook, they might give you delta S naught, okay? The sum of the delta S naught. Both work perfectly fine. So here, if we were to look at the sum of the S naught, the products, what I would do is I would do 3 times sulfur, which is the rhombic. If I were to take a look at sulfur rhombic, which would be 32 joules per Kelvin per mole, plus water gas, so 2 times for water, which is a gas, 189 joules per Kelvin mole. And what I would get here, 2 times 3, so I would get 474 joules per Kelvin. If I did the sum of the entropy for the reactants, I would have 2 times H2S. So H2S, if I take a look, come on, where's hydrogen sulfide? So 2 times 206 joules per Kelvin mole, plus sulfur dioxide gas, plus 248 joules per Kelvin mole. Oopsie, out of space. And then what I have is 2 times 206 and 248, so 660 joules per Kelvin. So delta S naught is equal to 474 joules per Kelvin minus 606 joules per Kelvin. And I get an answer of negative 186 joules per Kelvin. Okay. So that is a summary of how to calculate entropy. All right. What I'm going to do is I'm going to pause it here. I'm going to stop it here. And I'm going to give you some homework assignments for you to take a look at and try out. And then what I'm going to do in my next video is talk about something called Gibbs free energy, which takes this idea of entropy and the idea of enthalpy and merge it together to determine equilibrium. All right, folks, thank you. Have a